Hey everybody, Grace Joseph from class asked, how do you know what to do? Well, the first thing you do is you get the ferret to get the food away from your math problem. Let's go, come on. So I've got two problems here, the 10 to the x equals 17, 9 to the x equals 17, and one of them is nicer than the other, even though they look like they're the same problem. The 10 to the x is the nicer one because we have a button on the calculator for logs to the base 10. So this one's actually the easier one to do because that one you could literally rewrite it using rules of logarithms that if you have 10 to the x equals 17, it's logically equivalent to log to the base 10 of 17 equals x. And you have a button for log to the base 10 of 17. You can actually do the problem right now. Now the other thing you could have done was take the logs of both sides. So I have the word or there. Take the log of both sides. Are you feeding her?
She's mumbling the original.
Okay. All right. So anyway, so we have take the log of both sides of this same equation. The x comes down. So you can have the x come down and do this. Or you can look and see log to the base 10, that's of 10. These two undo each other and you get x. Whichever way you're thinking of it. You can even use natural log. You don't even have to use log to the base 10, even though the problem's built for it, because you're going to have natural log of 17 divided by natural log of 10. So that comes out to be the same answer. These all come out to be 1.23. And you can check that by doing 10 to the 1.23 on your calculator. Of course, you won't get 17 exactly. It comes out to be like 16.98. But that's good. That means that the 1.23 is approximately correct. No matter which way you do it, you're getting an answer that works. Now the 9 to the x leaves you in a bit of a jam because the 9 to the x, you don't have a button for log to the base 9. So this one you have to take the log of both sides, and it doesn't matter whether it's log to the base 10 or natural log. It doesn't matter. You're going to have log of 17 divided by log of 9 after you bring this x down. You do log of both sides, the x comes down. Hi, weasel. And you get this number 1.2895. When you do log of 17 divided by log of 9, I would suggest you try that problem with your calculator. And when you do, you can check that answer. You can check that answer by just doing 9 to the 1.2895 on your calculator, and it's going to come out to be 17.001 or something. It's going to be really close because you gave it enough decimal places. So how do you know what to do when x is in the exponent position? Look, you're going to have to use logs at some point. You either take the log of both sides, or if the base is nice, you can go directly to a nice answer if you're pretty confident with your log rules. Another question, how do you know what to do, is what do you do when you got a bunch of letters? What do you do when you have everything's letters, like this kind of problem, and you will have a problem like that? Well, if you know your rules, or know, you don't have to have them memorized, but be able to use them, you might say, well, these are inverse functions, log to the base b and b to the something. These undo each other. The log and the exponential function undo each other. Should just be y. But let's say you're paranoid about it. Well, change all the letters into numbers, but be consistent about it. In other words, put the same number in these two spots and be smart. What base do you have a button for? You have base 10. So make both of those b's a 10, and don't make y a 10. Make it something else. And then I'm going to do on my calculator right now, I'm going to do log of 10 to the 5th. Let me show it to you. So here's my log of 10 to the 5th. I'm going to hit enter, and it comes out to be that 5. See that 5? So what you're supposed to do from here is, if you did this problem off to the side, you'd say, well, the answer came out to be just this 5. I bet this answer is just the y. And you get it right, even if you're not so good with the log rules. So another piece of advice to you is, how do you know what to do when it's one of these alphabet soup, letters everywhere problems? Change the letters into numbers that you can do in a problem on your calculator and get somewhere. What do you think, Weasel? Is that pretty good? All right, one more problem. And this one I stole right out of the news. So here's from day 10 being the day we had 25 deaths in the United States. So that's day 10. No, sorry, that was day 0. Day 0 was 25 deaths. So day 10 was 10 days after 25 deaths. We had 60 deaths. And then day 14, 200 deaths. So that's a pretty fast growth. You can use your calculator to do the regression equation. It's exponential regression. I did it and here's the equation I got. I'd like to check this equation against day 19 because I can get day 19 data. On day 19, there's approximately 750 people dead. So that's actual data. I'm going to check my equation against that. So you put a 19 right there because X is days and Y is deaths. So you put the 19 right there, 1.35 to the 19, and then multiply by 2.96, and you get 887. So it's to be expected because exponential models grow like rockets. And epidemics don't have this kind of curve because eventually they top off. Eventually they top off when you've reached the point where just about everybody who's going to get it has got it. So they don't have a straight up growth that's unlimited. So just think about it. I mean, there's only a finite number of people to die. You can't just keep going up like a rocket. So exponential functions like this are bad models for long term. So I'm not surprised that the actual data is lower than exponential. It's good news in the sense that maybe the quarantining is working a little bit, maybe. All right, so according to this crappy model, though, let's just pretend we're using this model. When do we have 300 million dead? Which is a terrible thing to ask, but you get a surprising answer. Let's do the math for 300 million dead. So you have 300 million dead, 2.96 times 1.35 to the x, and you're solving for x. How do you know what to do? Well, x is in the exponent position. We're going to have to use logs, but not first, because read the problem, 2.96 times 1.35 to the x. So you have to divide by that 2.96. So this is almost 3. Do you see it? So we get just slightly more than 100 million, because we have 300 million divided by almost 3. So I got 101 million. And now you take logs of both sides, and x is equal to the log of 101 million divided by the log of 1.35, which surprisingly comes down to be 61.4 days from day 0. Oh my God, we have 61 days. That's 2 months, kids. But nobody, even the worst news people, are not reporting this kind of math because it's just irresponsible. You're using this model for super long term, which doesn't apply. So there you have it. This model is not so good. It's good for short term, but not long term. You get scary numbers like this. We have 2 months. That puts us in what? June. You have till June. That's not the deal. All right, talk to you later.